Ever wonder how your brain instantly recognizes a cat? It's a remarkable feat of biological engineering, a process so seamless that we often take it for granted. No manual, no hesitation, it just knows. The moment your eyes land on those feline features, your brain fires off a complex series of signals, instantly categorizing and identifying the creature before you. Artificial neural networks, or ANNs, are inspired by this ability. They represent our attempt to replicate this incredible process within the digital realm. They're computer systems designed to spot patterns, much like we do. These networks are built to analyze information and extract meaningful insights, mimicking the way our brains process sensory input. But let's be clear, neural networks aren't actual brains. They don't possess consciousness, emotions, or the capacity for subjective experience. They're mathematical models, not squishy emotional thinkers. They operate based on algorithms and data, not feelings or intuition. Their real strength? Finding connections in massive amounts of data. They excel at identifying subtle relationships and trends that would be impossible for humans to detect manually. Imagine searching for a red grain of sand on a beach. With a billion tiny helpers, you'd find it fast. Each helper sifting through a small portion, quickly identifying and reporting back. That's how neural networks work. They break down complex problems into smaller, more manageable tasks, distributing the workload across numerous interconnected nodes. Instead of programming every rule, we show them thousands of examples, like teaching a child what a dog looks like by showing lots of dog photos. The more examples they see, the better they become at recognizing dogs in different contexts and situations. The network starts as a blank slate, then learns by example, apples versus oranges, cats versus dogs. Over time, it picks up on patterns and figures out the rules for itself. It identifies the key characteristics that distinguish each category, allowing it to accurately classify new data. This ability to learn from examples, not just follow instructions, is what makes neural networks so powerful. It allows them to adapt to new situations and solve complex problems that would be impossible to tackle with traditional programming methods. It's science in action, and it's changing the way computers learn. This paradigm shift is opening up new possibilities in fields ranging from medicine to finance, promising to revolutionize the way we interact with technology. Let's zoom in, way in, on the fundamental building block, the artificial neuron, a simplified version of its biological counterpart, but still a tiny decision maker. It's the core component of these networks. Each neuron gets information, assesses its importance by assigning weights, and decides based on those weights whether to pass the information on to the next neuron. It's a simple yes or no, but with weighted nuance. Neurons are organized into distinct layers: input, hidden, processing, and output. The input layer takes in raw, unprocessed data, like individual pixels from a digital photo, or words from a text document. The hidden layers then do the heavy lifting, the real computational work, finding subtle patterns and combining simple features into more complex, abstract ideas. The more hidden layers a network has, the more intricate and complex the patterns it can potentially learn and recognize. Finally, the output layer gives the final answer. Is it a cat or is it not a cat, for example? A simple binary choice. The whole process from start to finish is like a towering skyscraper. Data enters at the ground floor lobby, gets processed and refined on each successive level, and ultimately emerges as a clear decision at the very top. Each layer subtly transforms the data, refines it step by step, until the network finally reaches its ultimate conclusion. That's the secret sauce layers working in perfect harmony, collaborating to turn raw, unstructured data into smart, actionable answers. And that's, in essence, how these complex neural networks think and learn. So how does a neural network get smart? It's all about training, like a guessing game on repeat. The network makes a guess, gets feedback, and tweaks its internal settings, its weights, to do better next time. This process is called backpropagation. The network learns from its mistakes, adjusting itself after each error. The learning rate controls how big each adjustment is. Too big, and it overshoots. Too small, and it takes forever to learn. Training is a cycle. Guess, check, adjust, repeat, thousands or millions of times. With each round, the network gets a little smarter, fine-tuning its understanding of the data. Eventually, it can spot patterns and make accurate predictions, even on things it's never seen before. It's not memorizing, it's generalizing. That's the magic of neural networks learning from experience, not just rules. And that's how they become pattern-spotting pros. Learning in action. Neural networks aren't just science fiction, they're everywhere in your daily life. Your phone's camera uses them to recognize faces and tag friends in photos. Online translators use them to turn whole sentences into natural-sounding language, not just word-for-word swaps. Voice assistants like Siri and Alexa rely on neural networks to understand your speech and respond intelligently. They power movie recommendations, help doctors spot diseases in scans, and even drive self-driving cars. Neural networks are the invisible engines behind much of today's smart technology. They work quietly in the background, making devices more helpful and intuitive. The future is already here, powered by these learning machines, and they're just getting started. Not all neural networks are the same. They come in various forms, each designed with a specific purpose in mind. Just like different jobs need different tools, different problems require different network architectures. The feed-forward neural network is the simplest, the foundational building block. Data flows one way, like an assembly line, moving from input to output in a straightforward manner. Great for basic tasks like spam detection, where the relationship between input and output is relatively simple. For images where spatial relationships are crucial, we use convolutional neural networks, or CNNs. They scan pictures with filters, spotting edges and shapes, identifying patterns and textures, making them perfect for facial recognition, identifying individuals from their unique features. Or self-driving cars, where understanding the visual environment is paramount for navigation. When order matters, when the sequence of information is critical, like in language or music where the meaning depends on the arrangement of words or notes, we use recurrent neural networks, or RNNs, designed to handle sequential data. They remember what came before, maintaining a memory of past inputs to influence future predictions, making them ideal for translation, where the context of the sentence is crucial for accurate interpretation, and speech recognition, where the meaning of a word depends on the words that came before it. Each network type is a specialist, excelling in its own particular domain. Feed-forward for simple tasks, CNNs for images, RNNs for sequences. Choosing the right network is key to solving the problem, ensuring optimal performance and accuracy. Scientists are always inventing new architectures, constantly pushing the boundaries of what's possible. Pushing the limits of what these networks can do, unlocking new capabilities and applications. It's a family of learners, a diverse collection of algorithms, each with unique talents, each contributing to the overall progress of the field. The right tool makes all the difference, enabling us to tackle increasingly complex challenges. That's what keeps this field so exciting, the constant potential for new discoveries and innovations. The possibilities keep growing, expanding our understanding of intelligence and computation. Neural networks are powerful, but they have real limitations. Data bias is a big problem. If the training data is biased, the network will be too. The black box issue means we often can't explain why a network made a certain decision, which is risky in fields like medicine or finance. And remember, neural networks aren't conscious. They don't think or feel, they just mimic patterns in data. They're brilliant imitators, not thinkers. Researchers are working to make AI more transparent and fair, but challenges remain. We must use these tools thoughtfully and ethically. Understanding their limits is as important as knowing their strengths. Science is about asking not just what we can do, but what we should do. The most important ingredient for a neural network: data, lots of it, and high quality. A network is only as good as the data it learns from. Bad or biased data leads to bad results. To teach a network about cats, you need thousands of diverse cat images, and plenty of non-cats too. The explosion of digital data and faster computers has fueled the rise of powerful neural networks. More data means better learning and smarter models. Neural networks reflect the world we show them, so the data we choose matters. They're reshaping everything from science to entertainment. Understanding how they work helps us use them wisely, and that's the real power of this technology.